All right, chemistry. Let's finish up chapter 8. Remember, we are combining sections 2 and 3, so this is part 2 of your video lecture for sections 2 and 3. Last time, we covered synthesis reactions, decomposition reactions, and single-displacement reactions. Today, we're going to finish up with double replacement reactions, and if you're paying attention and have a decent command of a single displacement, a double displacement isn't going to be any trouble for you at all. But we are going to add this idea of a combustion reaction and what it actually means. And then lastly, what we haven't done yet is try to predict the products of simple reactions if we're given the reactants. Okay, so that's how we're going to finish up. Let's fast forward to slide 20, because that's where we left off. All right. Let's see. Almost there. There we go. Okay. Double displacement reactions. Double displacement. If we go back just a few slides and we start talking about single displacement, and here I'm just going through all these different examples of what a single displacement is. A single displacement reaction, also known as a replacement reaction, so you might hear me say that, just be aware. One element replaces a similar element, and the big takeaway here is we're noticing that there are two elements, A and B, that are similar to one another. X is also here, but it's not similar. And what we mean by that is, for example, A and B are both potentially going to act as a cation, meaning they're two metals. Okay, it's a lithium and a magnesium. Is this going to happen? Oh yeah, they're similar metals, so there may be a displacement reaction there. You're never going to have a metal and the non-metal change places. Okay? You're never going to have that replacement, because then you would have two metals bonded together. And that's not going to happen in this type of replacement reaction that we're talking about. But the overall form that we're looking at here is a monatomic and a binary. Reacting to form a monatomic and a binary. Let's remember that. Monatomic, binary, monatomic, binary. And so when we go to our double displacement here, the ions of two compounds. With the single displacement, there's only one compound and then one lone ion over there. But here in the double displacement reaction, the ions of two compounds exchange places in an aqueous solution. And this is always happening in an aqueous solution, by the way. So it's always in water, dissolved in water, to form two new compounds. Okay, so you have two compounds to start. You have two compounds to end. The way that's different from a single displacement, you have one compound and a monatomic there. You have a monatomic and a compound. Here, you have two compounds on both sides of the reaction arrow. In these types of reactions, one of the compounds formed is usually a precipitate or some sort of insoluble gas that bubbles out of the solution, or maybe just a molecular compound like water. Okay, especially when we start dealing with reactions with acids, a lot of times water is going to be one of the products. The other compound is often soluble and remains dissolved in solution. And so what you're taking away from these two bullets is when you have a double displacement reaction, very often one of the products is going to have a state of phase other than aqueous, and the other will still be in aqueous, right? So you got one aqueous and one non-aqueous. Usually, this happens very, very commonly. All right, so looking at that general equation, this is the big thing that you want to commit to memory, that you want to stick into those little brains of yours. The general format. Notice we have binary, two binaries on one side, one binary, two binaries on the other side. And remember, you're only having like elements replace like elements. So in this example, A is only going to potentially replace B. Y is only going to potentially replace X. Okay, we're never going to have, on this other end of the reaction, on the product side of the reaction, we're never going to have an AB and then an XY. Okay, we're never going to have similar elements together because those are the ones doing the replacing. Okay, because again, these are ions here. These are ions in solution. AY and BX represent ionic or molecular compounds. All right, so like we said, very often double replacement reactions involve the formation of a precipitate. Remember, that's actually one of the observations that you can make that suggests that a chemical reaction has taken place. The formation of a precipitate occurs when the cations of one reactant combine with the anions of another reactant to form an insoluble or only slightly soluble compound. Now, insoluble means it's not going to go into solution. It just won't. Slightly soluble means it can go into solution if you add a significant amount of kinetic energy, whether you heat it or just simply agitate it mechanically. But in that current situation, it's going to come out of solution because it's only slightly soluble. For example, right here we have potassium iodide and lead nitrate. Now remember, we can figure out whether or not some of these elements are going to replace one another. For example, if potassium is going to replace lead, we can do this simply by looking at the periodic table and the trend. Things that tend to be things that are above other elements on the periodic table tend to be able to replace them because they're more active. But notice we have two species, and they're both binary. Okay? Both binary. That's why it's a double displacement. But they're both aqueous. Both of these binary compounds are in the aqueous state. We have one aqueous state binary compound on the product side, but the other binary is a solid. Okay, this is a solid. This is a precipitate. Remember, this solid, everything else aqueous, that means this is a precipitate. The precipitate forms as a result of the very strong attractive forces between the lead cations and the iodide anions. One of the things that we'll cover in AP chemistry, if you guys choose to go that route, is exactly what is happening when you dissolve, like physically, is really zoomed up on an individual molecule basis. What is happening in this dissolution event? Well, it's actually being surrounded by water molecules. They're being kind of ripped apart by the polarity of the water molecules. But if the attraction between the two is of a certain strength, it won't allow the water to get in between those bonds and break those bonds with its polarity. It'll just remain a solid. It won't actually be pulled apart. And so it is in a solid state. One of the things that you'll also find on the product side is a gas. Okay, in the same way, these bonds are going to be pretty darn strong. It's just that at room temperature, this compound is not going to be a solid. It's going to be a gas. But this happens quite a bit when you introduce things like a solid into the aqueous solution. Gases often result. So we have our iron sulfide, or iron 2 sulfide, I should say, be specific. It's a solid. We're going to mix it into solution. So we already have some hydrochloric acid there mixed in the water. Going to mix this up, and as a result of the reaction, we're going to get a gas and then some iron 2 chloride, but the iron 2 chloride remains in solution. We're going to have water. Okay, this happens a lot when we have reactions with acids and bases. Okay, acid, base, acid, base. So when these two things react directly together, we get a salt and water. Okay, a salt, remember, is simply another term for an ionic compound, but we get a salt and then we get water. That's indicative of an acid-base reaction. But what we want to pay attention to here for our purposes, we have aqueous plus aqueous, binary plus binary. On the reactant side, go over to the product side, we have binary and binary. One aqueous, one liquid. Okay. All right, that's it for double displacement. Let's move on to combustion reactions. Combustion reactions tend to confuse a lot of people. One of the reasons is those students who are super on their game, they remember the equation for cellular respiration from biology. Okay, and this is actually an example of a combustion reaction. And so they think that carbon dioxide and water both have to be present. Okay, have to be present. Now, quite often they are, but not always. So let's pay attention to the very strict definition of a combustion reaction. In a combustion reaction, a substance combines with oxygen. The substance combining with oxygen, releasing a large amount of energy in the form of light and heat. And so notice here, we're not saying anything about water. We're not saying anything about carbon dioxide. The only requirement for it to be a combustion reaction is the substance combining with oxygen. So let's look at an example here. Example, hydrogen combining with oxygen. This is a combustion. But look at the products. There's no carbon dioxide. There's no carbon dioxide here. Why isn't there any carbon dioxide? Because there's no carbon source on the reactant side. Okay, so we're combining this oxygen with whatever is here, and that's hydrogen. We're making some water. Okay, combustion of hydrogen makes water. Here's an example that does have both carbon dioxide and water in the products, combustion of propane. And here is what you were thinking when you think, oh, combustion is going to yield carbon dioxide and water. You're thinking about hydrocarbons. When you combust hydrocarbons, when I say hydrocarbon, there's a hydrogen and carbon in this substance that we're combining with oxygen. When you combust a hydrocarbon, yes, you will get carbon dioxide and water, but only if there's both carbon and hydrogen. Look up here in the example for the combustion of hydrogen. There's no carbon source, so there's not going to be anything to make a carbon dioxide out of. Similarly, and this is actually one of the problems on your worksheet, is we're going to oxidize a carbon, like just pure carbon. There's no hydrogen there. So in your products, you aren't going to have water because there's no hydrogen source. You're only going to make carbon dioxide. All right, Robot Lady has something for us, so let's see how that goes.
Methane, like many fossil fuels, can react with oxygen in a combustion reaction, releasing heat and forming carbon dioxide and water. The amount of oxygen available is very important for this reaction. When the supply of oxygen is limited, carbon monoxide, a poisonous gas, is formed. At very low oxygen levels, soot, or tiny pieces of carbon, are formed.
Thank you, Robot Lady. All right, so we have covered all the 5 types of reactions that we are going to cover in from section 2, and here's a very simple diagram to go over those. We have a 5-pointed star. Each point represents one of our reactions. We have combustion, decomposition, synthesis, single displacement, double displacement. And we have the key characteristics that we are supposed to be associating with each of those reaction types. So as you guys are prepping for this last chapter test, this is your friend for section 2. Please make yourselves aware of this diagram. And the last thing we're going to do for section 2, we're going to try to identify reactions and predict the products. Okay. So here is a list of steps. It's a multi-step. It's going to go through a couple different slides, so bear with me. Number 1, is there only one reactant? Okay, if the answer is no, you can skip to step 2. If the answer is yes, it's a decomposition, that's a new one, decomposition reaction. Okay, if there's only one reactant, the only thing it can possibly do is break down. So a binary compound generally breaks down into its elements. Anything larger, you're going to have to go through some other specifics. I'm only going to give you the binary compounds. I'm not going to give you something typically very large and complex. But if there are 2 reactants, go to number 2. Are the reactants 2 elements or 2 simple compounds? I'm sorry, or 2 simple compounds. If the answer is no, okay, if they're larger than that or complex, go to step 3. But if they are just elements or very simple compounds, you probably have a synthesis reaction. Okay, if both reactants are elements, the product is simply going to be the binary compound. If you have a metal reacting with a non-metal, use the expected charges, right? Ionic charges must balance to predict the formula and the compound. So we're really just using ionic charges to make sure that we're balanced up. If the reactants are if the reactants are compounds, the product will have a single ternary, okay, like more complex compound, according to the guidelines that we're not actually pushing that hard this section. So number 3, are the reactants oxygen and a hydrocarbon? Yeah, I hope that reminds you of combustion. If not, go to step 4. But if the answer is yes, you have a combustion reaction. The products of a combustion reaction with a hydrocarbon are going to be carbon dioxide and water. Are the reactants an element and a compound other than a hydrocarbon? If yes, you probably have a displacement reaction. So an element and a compound, an element and a compound, binary, you probably have a displacement reaction. Use the activity series, which we're really going to hit in section 3 here in a couple of slides. If the more active element is already part of the compound, then no reaction will occur. Otherwise, the more active element will displace the less active element. And lastly, are the reactants two compounds composed of ions? Okay. If it is, you probably have a double displacement reaction. Write the formulas of the possible products by forming the two new compounds from the ions available. Just switch partners. All right, let's see. We got some. I was supposed to cut that out. Ignore those. Objectives for the last section for Chapter 8. Explain the significance of an activity series, and use an activity series to predict whether a given reaction will occur and what its products will be. Now here, going back to our last couple slides where you're asking yourself these questions, is this present? No. Is this present? Yes. Then this is probably going to happen. We're doing that process here, but now we actually are going to talk about the tool, the activity series, quote unquote, more active or not. We're going to talk about that specifically. So the ability of an element to react is referred to as the element's activity. The more readily an element reacts with other substances, the greater its activity is. So we don't necessarily say reactivity, we just say activity. An activity series is a list of elements organized according to the ease with which the elements undergo certain chemical reactions. For example, for metals, greater activity means a greater ease or a loss of electrons to form positive ions, cations. Remember, in order to satisfy that octet rule, metals tend to lose their electrons. So how easily are they going to lose electrons? Not all of them lose electrons with the same ease. The metals that lose electrons more easily are more reactive and are said to have a greater activity. For nonmetals, it's the opposite. Flip it. Right? So, for example, fluorine is going to gain that one electron very, very aggressively. Actually, in fact, more strongly than any other element out of the nonmetals. So it is the most active nonmetal. The order in which the elements are listed is usually determined by single displacement reactions. And now that's just a factoid. You're not going to have to use that for problem-solving situations. It's just a factoid. I may ask you this directly on the test. It's a possibility. But the activity series is actually based on experimentation. They actually do single displacement reactions to see if the lone element is more active than the element in the binary compound or not. Now, the most active element is placed at the top in the activity series. That means an element on top can replace each of the elements below it to form a compound in a single displacement reaction. The activity series are used to help predict whether certain chemical reactions will occur, and you will have to do this on your test and on your quiz. So here are the activity series. So there's an activity series for metals. We tend to use this a little bit more because there's more data on this. There are more of them. But lithium, according to this chart, is the most active metal. It will replace anything and everything that follows after it. Down here, we have gold, silver, and platinum. These are the least active. They're fairly unreactive. The only way you can get them to react generally is to react them with oxygen, which is highly reactive, by the way. But even then, it only happens indirectly. You almost have to trick it. We also have an activity series for nonmetals. Typically, we kind of stick with just the halogens. We don't deal too much with the nonmetals, but it works in the exact same way. Fluorine can replace anything below it. Chlorine can replace anything below it. Bromine can displace iodine, and iodine is just getting booted all over the place. All right, Robot Lady, what do you got for us? Finish this up.
An activity series is a categorization of elements based on their reactivity. For example, alkali and heavier alkaline earth metals react readily with cold water, oxygen, and acids. Lighter alkaline earth metals, aluminum, and some transition metals will not react with cold water but will still react readily with steam, oxygen, and acids. Some heavier metals will react with acids and oxygen but are unreactive to any sort of water. Other heavier metals will react with oxygen but are inert to acids and water. A few transition metals, such as gold and silver, are very unreactive.
All right, chemistry, you have just finished Chapter 8 notes. I will see you next period.